Okay, we're going to continue our discussion with graphing functions by hand in section 3.2. What our main focus on in section 3.1 was using the first derivative. Okay, using the first derivative. And we had said in that section that the first derivative was really helping us figure out what the slope was like on the curve and where any maxes or mins were located. We called those critical values. Those are our extreme points, okay? But what we're going to be doing in this section is we're going to be, in addition to what we did in the first section, we're going to add to that using the second derivative, and the second derivative is going to help us find the curl or the concavity of the curve, okay? And that's going to uncover something called an inflection point, which we're going to look at here. Okay, now when we talk about the curl and concavity, we're talking about graphs that are either curled like that, or if a graph is curled like this. Okay, you can see this in this picture here below. Okay, a curve that curls upward is said to be concave up. So I'm just going to shade over top of the section of this graph that would be concave up. And then a curve that curls downward is said to be concave down. Okay, so I want you to kind of think of it like this. If you were to spill water on top of your graph, any section of your graph that feels like it would hold some of the water is considered concave up, whereas any section of the graph where it feels like the water would run off of it, that is considered to be concave down. Now, in terms of an inflection point, okay, an inflection point is that specific point where the concavity is changing from either being concave up to being concave down or vice versa. So you can see when I kind of color-coded this here, this point right here is considered to be the inflection point because we're shifting from being concave up to the graph now being concave down. Okay, in terms of just a line that is just linear, a straight line like this, a line like this has absolutely no concavity to it at all. Okay, and so the second derivative is going to help us figure out whether the graph is concave up or concave down. Now, if you remember, in our first derivative sign diagrams, anytime we said the first derivative was greater than 0, that meant the slope was positive, and anytime the first derivative was less than 0, it meant the slope was negative. And at those critical values, where the slope of the derivative actually equaled 0, that's where the slope was 0, or the top of a curve, or of a max, or the bottom of a min here. Okay. Now, when we look at the second derivative, okay, looking at the second derivative being greater than 0 or the second derivative being less than 0, this is going to indicate what the concavity is, okay? And if the second derivative at a particular value is either 0 or undefined, that means it might indicate an inflection point. Now, I just want to chat through with you why, if the second derivative is greater than 0, we say the curve is concave up, versus if it's less than 0, it's concave down. You can see these two pictures here. We'll look at the one at the left here first. As you look at this one on the left, you can see that the curve itself is definitely, like, there's a min down here, okay? And clearly we would designate this as being concave up. If we dumped water on this curve, it would hold all that water. That's what we mean by concave up. But I want you to look closely at these 5 points here. And if you look really close at the graph, you can see a tiny tangent line was drawn at each of those points. And what I'm indicating is I'm indicating what the slope is of that tangent line at that specific point at the curve. So you can see these tangent lines over here on the left, they are negative. This one's really steep, -2, not quite as steep, -1. I get down here, the slope's horizontal, 0. Now on this side, look at what my slope is. It's 1, and now here it's +2. Well, remember when we did second derivatives back in chapter 2, we said that the second derivative described how the first derivative was changing. And we looked at that in the context of a distance function. The first derivative was velocity. The second derivative, we called that acceleration because it was describing how the velocity, the first derivative, was changing. Well, in this context, again, your second derivative is still going to be describing how the first derivative is changing, but our first derivative is representing the slopes. Okay, so let's look at these slopes, and we want to kind of look at the slopes as we travel in the direction from left to right. So as you look at these slopes, -2, -1, 0, 1, and 2, how are the slopes, the first derivatives, changing? Well, it looks like they're getting bigger as we move from left to right. So our interpretation of this graph, if we say that the second derivative is greater than 0, that means the second derivative is increasing. We're showing that the slopes are getting bigger. That means that the graph, or it's concave up. Okay, if your slopes are getting bigger, it's concave up. So we want to always connect. If the second derivative is greater than 0, we're always going to conclude that means concave up. So let's look at the same thing over here. Again, we're just looking at these 5 points. Clearly, this graph is concave down. If you look at the slopes, you can see here what are happening to the first derivatives. Again, as you move from left to right, so we're traveling from left to right. Now the slopes are big, but now they're getting smaller as you go from left to right. So I'm going to describe here my second derivative is less than 0. Anytime your second derivative is less than 0, that means the graph, or it's concave down. Okay, so we want to connect that if our second derivative is less than 0, that section of the graph is concave down. Okay, that's going to be important when we're graphing these by hand here. Okay, so you should have been given this handout here titled The Official Steps for Graphing by Hand. Okay, you'll notice there are 8 steps to this. This is going to replace the steps that I had given you before. Okay, this is going to include the second derivative and the concavity here for these graphs. Now, just to kind of simplify things a little bit, for the moment, we are not going to be dealing with anything involving asymptotes, so you don't have to worry about this top part here. We're just going to begin with step number 1, which is to find the critical value by setting the first derivative equal to 0. You notice these steps are going to sound, they might be a little bit in a different order than what they were on the other page. But what you're going to notice is steps 1, 2, and 3 are going to be mirrored in steps 4, 5, and 6 for the second derivative. Okay, so I'll just keep flipping back to this, and we can reference these steps as we work through this next example here in the notes. But our first step is to find the critical values by setting the first derivative equal to 0. Okay, so on this particular problem, it's a word problem, but it just says that a company's annual profit after X years is given by this function here in millions of dollars. We are wanting to graph this function by hand here. Okay, so our initial step, I'll just label this step number 1, is going to be to take the first derivative. Okay, pretty easy function to take the first derivative with the power rule here. Okay, this feels exactly like what we had done in the past. Okay, we're then going to set that equal to 0, and I'm going to factor my derivative. I'm going to check for a GCF first. It looks like maybe there's a 3 that we could remove from each of our terms here. Okay, now we want to look at what we have left here and see if there's any way we can factor this trinomial further. Remember, if your lead coefficient is a 1, we can factor this by just making 2 sets of parentheses, x here and here. We want to think of 2 numbers that are going to multiply to be a times c, that'd be 8, but add together to be the b, that would be -6. Okay, those 2 numbers should be -4 and -2. Okay, so we'll put 1 here, one here. I'm definitely going to be putting a star next to this step because I want to come back to my factored form of my derivative when I'm doing my first derivative sign diagram. Okay, I'm going to go ahead and identify my critical values are x equals positive 4 as well as x equals positive 2. And I'm going to box that in. That is step number 1. Okay, you can see off to the side here I also have the steps listed here. So step number 2 is for us to find the critical point by substituting that critical value into, very important here, into the original function. Okay, we're looking for the y value that is going to be on the graph that goes with these critical values, these x values here. Okay, so we're going to take the original function, we're going to substitute a positive 4 in, substitute a positive 2 in. You can see that we get 16 back out for the 4 and 20 back out for the 2. So I'm going to label this CP for critical points. These will eventually be the points that I will be putting on my first derivative sign diagram. Okay, step number 3. Okay, step number 3 tells us over here that we are going to be making that first derivative sign diagram to figure out where there are maxes, where there are mins, and what the slope is doing. Remember, our first derivative is telling us what the slope is. All of this so far should feel very familiar, things that we did from section 3.1. Okay, so we're going to make a small horizontal line here. We're going to place our two critical values. One, we're going to say f prime 2 equals 0. You want to put the smaller of the two critical values on the left. And then f prime of 4 equals 0. That's going to go on the right. Okay. Now I'm going to go back. I'm looking for that green star that I filled in there. Okay. If you look where that green star is, I have 1, 2, 3 factors. So in each of these intervals, I'm going to put 3 sets of parentheses that are being multiplied together. As I look closer at my factored form of my derivative, I see the first factor is a positive 3. There is no x with that. So I'm just going to leave that first factor locked in as being a positive. Okay, the other two factors have x's, so I'm going to need to choose a test value within each of the intervals. So we'll start with this left interval. This vertical line here represents where x is 2. I need to pick something smaller than 2. I'm going to choose 0. If I plug a 0 into my second factor, this is going to come back as a negative. If I plug 0 into the third factor, I'm also going to get a negative. So now if I were to multiply a positive and a negative and a negative, and I'm just going to write this underneath here, the overall sign would be positive. Okay, remember, we also label, that's telling us then that the first derivative is greater than 0. I would draw an arrow going up. Okay, directly underneath where I'm saying the critical value of 2 is, that's where the slope is 0, so I'm putting a flat horizontal line. Okay, now I'm going to move to the next interval. This represents numbers bigger than 2, but smaller than 4. So I'm going to choose 3. Okay, I'm going to plug a 3 into my second factor. Looks like I'm going to get back a negative. I'm going to plug 3 into the third factor. Looks like I'm going to get a positive. All right, so I'm multiplying a positive, a negative, and a positive. So I'm going to be getting a negative. That tells me my first derivative in this interval is less than 0. I'm drawing the arrow going down. Okay, now I'm underneath the other critical value of 4, which is where we said the slope is 0. So you're going to draw a flat horizontal line. We have one more interval to do here. I need to choose a number that is bigger than 4, so I'm going to pick 5. 5 gets plugged into my second factor. Looks like I'm going to get a positive. If I plug 5 into my third factor, I'm also going to get a positive. So 3 positives multiplied together come back as a positive. The slope here, greater than 0, arrow goes up. Okay. All right, I already have the critical points. I think when we did this before, the steps were in a slightly different order. We had done step 1, maybe we had done the sign diagram, and then we did our critical points. Okay, I already have my critical points. Those need to be placed on my sign diagram here. This would be the point 220. I'm going to call that a max. This would be the point 416. I'm going to call that a min. Okay. Now, it would be called an inflection point if, like, this went up, flat, and then it was up on the other side. I'd label IP here for inflection point. Okay. All right. Now, here's what you're going to notice. I like to kind of do the work here in two columns. I like to do 1, 2, and 3 down the left side, and then 4, 5, and 6 down the right side, because step 4 mirrors step 1, 5 mirrors step 2, and 6 mirrors step 3. What we're going to do now is the same thing we did in steps 1, 2, and 3 with the first derivative, only we're going to be doing it with the second derivative. Okay, so for step 4, it says right here, find more critical values by setting the second derivative equal to 0. Okay, the second derivative. So here's my second derivative. It's going to be 6x minus 18, and I'm getting that from looking right over here. I'm taking the derivative of this. Okay, I'm going to set that equal to 0. I'm going to look for a GCF. Very easy here. I'm going to put a star next to the factored form of my second derivative, and I'm going to label the critical value is just x equals 3. Okay, you really don't know that something is an inflection point until you have done the second derivative. That's where the inflection point kind of becomes unveiled. Okay, so step number 5 is to find the critical point that goes with that critical value there. So we're going to take 3, plug 3 into the original function. We can see we get an 18 back out, so I'm going to label, here's another critical point, 3, 18. Okay. All right, now we're going to make, in step 6, what is called a second derivative sign diagram. Okay, it is made much like the first derivative sign diagram, only a few of the labels are a little bit different here, so make sure you pay attention to this here. I have one critical value, so I'm just going to put one dotted vertical line. Remember that critical value was at 3. I'm getting that just from right up here, step 4 here. Okay, at that critical value, that is where my second derivative is 0, so I'm putting a 0 there. I'm going to go back and find my yellow or green star here. I have two factors, the 6 and then also the x minus 3. So just two factors. The 6 I can lock in as being a positive. Okay, the other one I'm going to have to choose a test value. So I'm going to pick a number on this side smaller than 3. I'm going to pick 0. If I plug 0 into that factor, the second factor is going to come back as a negative. That means that overall, remember this is not the slope anymore, my second derivative is negative, which means it's less than 0. Now, I'm not drawing arrows here, okay? This is the part that's a little bit different on this. Do not draw an arrow down. Okay, I'm going to flip back to this front page here in the notes. Remember what we said. If your second derivative is less than 0, what does that tell you? It tells you the graph is concave down if it's less than 0. So what I want you to write on this sign diagram is I want you to write concave down. Okay, write concave down. Okay, now we're going to come over on this side. We need to pick a number bigger than 3. Let's pick 4. We plug 4 into that second factor. It looks like we get back a positive. So two positives multiplied together make a positive. So on this interval, my second derivative is greater than 0. Well, anytime the second derivative is greater than 0, that's when the section of the graph is concave up. Okay, now you're not drawing a flat line in between here, but you are looking if the concavity switched from down to up or from up to down, it means this point that's in between here, the point 318 is an inflection point. So I want you to label the point 318 there, and I want you to label that IP as an inflection point. Okay? Okay, step number 7, you can see over here, is to find the y-intercept. Okay, that is merely to just substitute a 0 into the original function for all the x's. It looks like we get back out a 0, so the y-intercept is at 0, 0. Okay, what you're going to do next is the same thing we did before. You're going to look at all of your critical points from the first derivative sign diagram, the second derivative sign diagram, and your y-intercept. Pick a scale to count by. I'm just going to count by ones on the x-axis. Maybe I'll count by fives on the y-axis here. Okay, we are now going to plot our points. Okay, so 220, as you plot them, you are labeling the coordinates and you are identifying what that point is. So I started over here, plotted 220, that's a max. I'm going to plot 416. We're going to call that a min. I'm going to plot 318, and I'm going to call that an IP, inflection point. And then finally, I'm going to plot a point at 0, 0, and call that the y-intercept. Okay, now I'm ready to graph, and you're going to have to collectively look at both your first and second sign diagram to get this right here. We can kind of see the ebb and flow of how the graph should be down, up at a max, down at a min. We want to make sure we get the concavity right. Everything to the left of this point, 318, needs to be drawn so that it looks like it's concave down. Okay, so it's going to look something like that. And then once I get on the other side of the point 318, now it's going to be sketched concave up, something like that, okay? And that's kind of the process here of how to go through. I really like these steps, and this replaces the steps that I had given you before here. Okay, we will do more examples of this in the coming days, but we're just going to close out here with a look at just two more quick things, but not fully graphing anything with the full 8 steps here. Okay, the question here is, for each curve, is there an inflection point? So essentially it's asking, is this point an inflection point, and is where this is pointing an inflection point? And the question you have to ask yourself is, what is the concavity on each side of that point? Well, it feels like the concavity here is concave up. It feels like on this side it's also concave up. So the concavity is not switching for this. So I'm definitely going to call this not an inflection point. We're going to say no. Okay, now here it feels like this is concave down, and when I get over here, maybe this is going concave up here. So on this one, I'm going to call this yes, okay, because this was concave down, and then here I'm concave up. Inflection points are when the concavity changes. Okay, the last thing that we're going to do here today is kind of fill in some inequality symbols that should go in between our first and second derivative and 0. I want to show you in each of these little graphics here how you could have slope that's positive and concave up, also slope that's positive but concave down. Okay, I want you to picture setting a car, it's terrible artwork here, on each of these curves, and the car's going to ride from left to right. Okay, in any of these scenarios where the car would be going uphill, okay, if you set the car on these two scenarios, that's what increasing means. It means your slope is positive. Okay, if your slope is positive, then that should be greater than. Your first derivative is describing slope. Your second derivative is describing the concavity. Now let's look at the concavity of this. This, if you spilled water in it, it would hold the water. This is concave up. That means the second derivative is greater than 0. Versus here, if you spilled water, the water would roll off. This is concave down. It's less than 0. Okay, in these last two pictures, again, a car, sitting a car and rolling it along from left to right. In both of these situations, the slope is decreasing. That means the first derivative would be less than 0. But in this third example here, this would hold water. This is concave up, so the second derivative is greater than 0. Versus here, the second derivative is concave down, so it's less than 0.